Before we go on, let us see some mathematical property of the scalar product of two vectors. From the definition of the scalar product of two vectors, we can see that it has the commutative property. Commutative property, that is, we have that A dot B is equal to B dot A. So the scalar product of two vectors is not depend on the order of the vector that you apply the operation. Okay, so it has a commutative property. Next, the scalar product is distributive. That is, if we have A dot with the vector B plus C, we can rearrange this operation to be A dot B plus A dot C. So we call that the scalar product is distributive. And from the definition, A dot B is equal to A B cos theta, where A and B are the magnitude of the vector A and B, and theta is the angle between these two vectors. So we must have that if A is perpendicular to B, theta is pi over 2, and cos theta is equal to 0, which means that A dot B is equal to 0. So when two vectors that perpendicular to each other, the dot product of these vectors will equal to 0. Next, if A and B point to the same direction, okay, so if we have A like this and we have B like this, so in this case theta is equal to 0, and we have that cos theta equal to 1, which means that A dot B equal to AB. Okay. The consequence is that if we calculate A dot A, that is the dot product of itself, we will have that is equal to the square of the magnitude of A. And it is obvious that now if A and B point in the opposite direction, we must have that A dot B equal to the minus of AB. Okay, so this is a basic property of the scalar product of two vectors. Sometimes it's more convenient to express the scalar product in terms of the component of the vector. So if we write down the unit vector along the x-axis, y-axis, and z-axis, and using the notation, this is I, this is J, and this is K. We can see that we have that I dot I is equal to J dot J and equal to K dot K, and they are equal to 1, right? Because the magnitude of the unit vector is 1. We also have that I dot J equal to J dot K equal to K dot I equal to 0. This is obvious because you can see that I is perpendicular to J and also perpendicular to K, and J and K are perpendicular. So the dot product of these vectors must equal to 0. From this relation, we can write down the dot product or the scalar product of two vectors in terms of its component along the x, y, and z axis. If we write the vector A as ax I plus ay j plus ac k, and also if I write b is equal to b x I plus b y j plus b c k. Now if I want to calculate the dot product A dot B using the commutative and distributive property of vector, we must have that A dot B is equal to ax bx plus ay by plus ac bc. Okay, so we can calculate the dot product or the scalar product of two vectors from their component in the rectangular system. An interesting consequence of this is that we can write down A dot A, which is equal to A square, and is equal to ax square plus ay square plus ac square. This is very useful relation.